Okay, so it's time for the last lecture before the Christmas break on proof complexity as a computational lens, lecture 16. We are going to talk about polynomial calculus space. So the agenda for today is polynomial calculus. Calculus space. We're going to focus on monomial space, but we're just going to define at the beginning what space measures one could study. We will start by a review. We only have one lecture on polynomial calculus space. We could have spent more time, so I'll review some of what is known. And then we'll just zoom into one result. Namely, we'll do a space lower bound for k-CNF formulas, random k-CNF formulas, for lower bound for random k-CNF. And as has happened several times before, for 2 CNFs, there should not be any lower bounds. For 3 CNF, random 3 CNF, there should also already be that hard. But it turns out that it's a little bit technically challenging. So if you'll cut me some slack and we'll just prove it for 4 CNFs, then we still get all of the interesting ideas will be there. We avoid the annoying technicalities. So again, what is the setting? We have we think of a polynomial calculus derivation as being a sequence of sets of polynomials. I'll refer to them often as configurations, which is, so every fat p sub I is the polynomials we have in memory at time I. And we can do, at every time step, we can do one of 3 things. We can do an axiom download. What are the axioms we can download? Some input polynomial from the formula, or we can also download Boolean axioms, or in polynomial calculus resolution, PCR complementarity axioms, saying that x and x bar are opposites. The proof, but even when we are in PCR, maybe this is a technical point that I should make clear. Even when we are in PCR, so PCR considers x and x bar, formally speaking, to be distinct variables, we will not consider them to be distinct variables. So whenever I talk about the truth value assignment, x and x bar are always going to have opposite values automatically. And all variables are going to be 0, 1 automatically. So although formally speaking, the Boolean axioms and the complementarity axioms are there, we really don't care about them. We only care about input polynomial axioms. And then we have inference, where you can apply. So axiom download is when p sub t is p sub t minus 1 union some axiom A. For inference, all we're really using is this semantic setting. We say, well, whatever the configuration is at time t is implied by what we had before. So we're actually going to mostly ignore inference steps. As we've seen before, this is both a strength and a weakness. So everything today will work in the semantic settings, where any length derivation you can have for free, as long as it's implicational. So our lower bounds will be in this very strong setting, but it also means that since we cannot really look at what's happening during the inference step, we cannot, for instance, get anything supercritical, which we did last time, but remember, then we worked very, very syntactically and really looked at the clauses in resolution. And then there's erasure. And erasure always saying just is that, well, p sub t is a subset, presumably a strict subset of p t minus 1. And what are we interested in measuring? We're interested in measuring the space. So every polynomial that we see, so lowercase p, q, r will in general be polynomials. I will write them as a linear combination of terms, and every term is a monomial multiplied by some feed element. And I think of all monomials as being distinct. Okay? So then we can define the line space of a polynomial is just 1. It's a polynomial. We can define the monomial space of a polynomial to be, if I goes from 1 to s, so there are s monomials in this polynomial, then the monomial space is s, and then we have the total space of a polynomial, and that will just be summing I goes from 1 to s, the number of variables in mi, which in polynomial calculus, although nothing forces us to have multilinear polynomials, we can assume this without loss of generality, because as soon as you pick up a power larger than 1 of some variable, we can use the Boolean axioms to remove it. So this is actually just summing up the degrees of the monomials. It's kind of the same thing. Okay, and now, given that you know this is how we measure for polynomials, then you can say that for a configuration P, flat style P, well, there's the variable space, which is just, you look at all variables that appear in P. But the other measures, the line space of a configuration would just be, well, summing up the line spaces of all the polynomials in P, and similarly, the monomial space of a polynomial configuration is just summing up for all p's in P the monomial space of P, and similarly for total space, we just go over all the polynomials and sum up the total space of all polynomials. Okay, and once we have this, now it's clear that for a derivation, the space of the derivation for whatever space measure I care about, just take the max over the derivation, and then given a set of input polynomials, today we'll focus on CNF formulas encoded into polynomials, k-CNF formulas. So the space of refuting a CNF formula is just take the minimum space for the measure you're interested in over all refutations, as we did before. Okay, so what will we be interested in? So it's not so hard to see. We talked about that in the multilinear setting, you can always refute any k-CNF formula in actually linear length. And if you sort of run that proof and you don't even need the multilinear setting, you realize that line space can, for k-CNF formulas or for CNF formulas, really can always be made constant. So it's not such a fun measure. But maybe we should just, this is why we don't care about line space. This requires a proof, but basically you go to the linear length proof in the multilinear setting in Mikša Nordström, and you study the line space of that proof. And you realize that there's nothing multilinear about the, I mean, you can, the multilinearization doesn't cost you extra space. Variable space is kind of a weak measure, and also we realize that this is anyway, I mean, this is resolution variable space, so we have no reason to go to polynomial calculus really to study this. So the two interesting measures that we really care about, or would be interested in, is monomial space and total space, where monomial space is the natural analog of closed space in resolution, because every clause turns into a monomial in polynomial calculus resolution. So this is what we'll care about, because we cared most about closed space for resolution. Another reason is that, well, we don't know really anything about total space. This is a big open. So let me tell you, so therefore, let me focus on monomial space. And let me tell you like a brief review of what has been known. So the space measure for resolution was defined by Turan, but then came Alekhnovich, Benselson, Rasboran, and Vigdresson, and realized that you can really lift this to any proof system, and they studied it also for polynomial calculus. And they gave the first lower bounds, but only for wide formulas. And the interesting thing is, so you get, from now on, whenever I say space during this lecture, unless otherwise stated, I mean monomial space. So they proved monomial space lower bounds for wide CNF formulas. And if you take the standard conversion with auxiliary variables to 3 CNF, these lower bounds break. And so this means that, but they prove tight results, for instance, for the vanilla pigeonhole principal formula, you get exactly up to constant factors, you get a linear lower bound n, regardless of the number of pigeons. But this is sublinear in the formula size. So far, only sublinear space lower bounds and only for wide formulas. Then came Filmus, Lauria, myself and Ron Sevi and Neil Fappen. This was in 2012, but the journal version is from 2015, where we had lower bounds for k-CNFs. But these were like basically just chasing, can we do something for k-CNFs? It's a specially tailored, kind of a slightly weird version of the pigeonhole principal formula that is built in an obfuscated way so as to get the space lower bounds. Some more things that this paper did is it showed that for space and size simultaneously, now the question is whether you care about whether you're doing polynomial calculus or polynomial calculus resolution. Because PC, as we know, could blow up pretty badly. So it's not even clear, like, can you do a linear space upper bound, worst case? The answer is for k-CNF formulas, you can do this. So you have the same worst case behavior as in resolution and PCR. Worst case, you can do simultaneous exponential size and linear monomial space, but that does require a proof. And this is from this paper. It's not entirely obvious. Then we have the interesting thing, actually, that if you look at monomial space, and now I focus on PC, importantly, not PCR, and I'm interested in the pigeonhole principal formula, n plus 1 pigeons say, and n holds. I really don't care about number of pigeons, so maybe I should write m here. Okay. And remember that I said if you turn this to a 3 CNF formula, then everything breaks, except that in PC it doesn't. In PCR, we don't know how to do this with dual variables, but without dual variables, we can get monomial space lower bounds for the vanilla pigeonhole principal formulas. And then we have this notion of weight constraint. So then what is going on? And another notion that is important is that of weight constrained CNF formulas. This is saying, suppose I have a wide class, A1 or A2 or all the way up to AW for some large W. Then I say that the formula is weight constrained if for any such wide clause I have all pairwise clauses not AI or not AJ. So this is saying basically that I know that this clause is going to be satisfied by setting exactly one betrothal to true, not more, not less. Okay, I don't know if weight constraint is a good name, but this is what we chose. And now the interesting thing that happens is if a formula is weight constrained, then in resolution, the clause space is the same, regardless of whether you look at the 3 CNF version or the wide version, except for a constant factor. And for PCR, you pick up a factor, a constant factor in front, but basically, let's see if I can type this. So the point is that asymptotically for a weight constrained formula, I don't care if you do the 3 CNF version or the standard version. This requires a proof, but it can be shown. Note in particular that the functional pigeonhole principle is weight constrained, right? what does this mean? This means that I'm sending every pigeon to exactly one hole. That's what the functionality axioms say. So this tells me that, well, we don't know how to prove, we still don't know how to prove really strong space lower bounds for the functional pigeonhole principle. But if you can do it, then it would work for the 3CNF version automatically. And then the important paper, like in some sense, the breakthrough paper, was by Bonacina and Galesi in 2013, and the journal version is from 2015, where they had optimal linear lower bounds for random k-CNF formulas. But not with 3, but with 4 and above. And they also had a general framework. That somehow, for the first time, they looked at this ADRW, they looked at Filmos et al., and somehow abstracted away what's going on and provided a very general framework. Basically, they're saying, like, here's a combinatorial object that you can build. And it's a kind of, for the prosecutor-defendant games and these prover-delayer games, it's kind of spoiler-duplicator games. It's sort of a game of that form. And if you have a winning strategy for the lower bound player in that game, then you just plug that in and you have monomial space lower bounds. Two more papers to go. So then, Filmos et al., again, with Lauria, with Lund and Mikša, and Mark Vinyals and myself. This was published this year, but the conference version was in 13, so it was right after Bonacina and Galesi. We did a bunch of things. So suppose that F is a k-CNF formula, just for simplicity. So one thing you can ask is this question we had. Atsiras Dalmau proved that width is a lower bound on space for resolution. You could ask whether degree is a lower bound for space in polynomial calculus, or maybe even resolution width is a lower bound for monomial space. What we proved is a very weak version of this. It's true if you allow for xorification. So you take the formula, suppose I have a width lower bound in resolution for this formula F, and now I take it and I do xorification. So I substitute every variable by 2 fresh variables. The XOR of those, I expand it out to CNF, and I look at the refutation of that formula. Then the refutation monomial space of the xorified formula is lower bounded by the way. But obviously we want the same formula on both sides, but at least this is something. And now this gives you immediately, if you plug this in to taking formulas, then you can get formulas. So then you can separate degree and size on the one hand and space in polynomial calculus, and you get even stronger separations than in resolution. So you separate space from size and degree, and let me just state roughly what I mean. So you have formulas such that the size of refuting them, even in PC, is essentially n log n, where n is the formula size. The degree of refuting them is constant. But the monomial space, even in PCR, is optimal, worst case, actually linear. So note that this is actually stronger for once you have, for resolution, we had length n, and that allowed us to get space n over log n. So here we're actually pushing the space all the way up to linear, at the price of getting an n over log n upper bound. We don't have anything like this for resolution. We don't know how to prove this in that sense. This is, morally speaking, stronger because once you have this, you can sort of, you could get rid of the log n here and divide down by log n there just by padding or something. In some sense, I'm being a little bit hazy here, but this is in some sense, you should think of this as a stronger result, I think, slightly stronger. The only caveat is that you prove this for its taking formula, so this will depend on the characteristic, which is not so nice. So I think in the literature, it's actually open to get this for formulas such that this holds in every field independent of the characteristic. Except that I realized on the way here today that I think that it should not be so hard if you just plug in other formulas, like so-called flow conservation formulas, or I think they're sometimes called end-of-line formulas, then I think you can get this independent of the degree. We should probably write this up before we make any formal claims. Maybe one way of doing that is to put this on the problem set. I think this should be doable. We also did some other things. So basically what this happens when you do this with secant formulas, you remember from last time, what you do is you take the graph and you make it into a multi-graph by just doing double copies of every edge. So what this results basically says, you have an expander graph, make double copies of every edge, and then you get the space lower bound you would expect. But what about secant if I just have an expander graph and no double copies? Well, then we're able to prove a slightly weird result. We can prove that if you have a graph of even degree, a regular graph of even degree, and if it's random, importantly, it needs to be an expander, but that is not enough. It also needs to be random. Then we get a square root n lower bound. And this basically comes from that you get a lower bound that is linear in n divided by, you need a cycle decomposition of the graph. You need to be able to divide all the edges of the graph into disjoint cycles to cover everything. Okay? And if you have and now look at that cycle cover and look at the longest cycle. Your lower bound is going to be, your space lower bound is going to be n divided by the longest cycle. Okay, and now you look at in a multi-graph like this, what cycles would you take? Well, you know, for any copy of edges, you take one edge and then you go back with the other edge. So now you cover all the edges by cycles of length 2, and that's why you get a linear lower bound. In general, in a random graph, cycles will have length, actually they won't have length square root n, they will have something like length square root n log n, but then you do a restriction argument because of course you can't live with losing this log factor, and then you get square root n. So the lower bound is like n over square root n, but it requires, the reason we need random graphs is that we need this good cycle cover. The fourth thing we do is we give a kind of barrier result for the functional pigeonhole principle. We look at this very nice, so one thing that you have, I think Bonacina and Galesi is a highly recommended paper, except that I'm being biased, obviously, but maybe we read this paper and we loved it, but we struggled a little bit. So in an appendix of FLM and V, we have like a write-up of Bonacina and Galesi that we found slightly easier to parse. So maybe like PG15 or the exposition of it in FLM and V25 is highly recommended reading, but what we show in FLM and V25 is also that this very, very nice abstract framework provably fails for functional pigeonhole principle. Because you need to build a certain combinatorial object. It's not a necessary condition for a lower bound, it's a sufficient condition for a lower bound. But this combinatorial object doesn't exist for functional pigeonhole principle. And then the final piece of news is a paper by Galesi, Kolodziejczyk, and Thappen, journal version also published this year. The conference version is from Fox 19. So you see, you had a kind of explosion in space complexity, algebraic space complexity from, well, essentially from 2012 to 2019, 7 years. And what they proved is, again, we recall that we're interested in how, assuming again that F is a k-CNF formula for simplicity, how is the monomial space of F, is it at all related to the resolution width. And it would be fantastic to get a greater equal, which would match sort of what we have for resolution. They don't give us quite this, but they give it with a square root clause. So they show that the monomial space of the refuting and k-CNF formula is lower bounded by the resolution with square root of that, up to some small constant factor. And this in particular means that now you can take any formula, Satan formulas, or functional pigeonhole principles, or anything for which we have optimal with lower bounds in resolution, and now you'll get square root n PCR space lower bounds. And that's where we stand. What they also prove, so we're gonna see that it's a very interesting paper. We'll talk about it after the Christmas holidays. They can, as a kind of warm up, they prove also for k-CNF formulas that actually the total space in resolution of refuting a formula is the width of refuting it squared, except for constant, which is a result that is originally due to Lauria Bonacina. So this says that if you have a strong width lower bound, not only we know by Atzera's Dalmau that a width lower bound implies a space lower bound, but not only that, in this large space refutation, you need many clauses and they need to be wide. So that's why you need W clauses, but they're also going to be on width of width W. With this, I think we have pretty much the lay of the land. Let me just state a few nice open problems. One thing is separating clause space and monomial space. So note that the way I define monomial space, I count the monomials with repetitions. But all the lower bounds that we're able to show are actually lower bounds for the number of distinct monomials. If your space lower bound only counts the number of distinct monomials, then already ABRW has a constant factor separation. They have a formula for which the space lower bound is n, but you only need 2/3 n distinct monomials. If you charge for repetitions, which I think you should do, then there's no separation. Nothing. Okay, so for all we know, maybe clause space and monomial space is the same. And I don't have a strong intuition. Like this is, I think it's fair to say this is a wide open question. Another favorite question, which I already told you about, is monomial space lower bounds for Pebling formulas. Meaning Pebling formulas where you do some kind of substitution, but you can do, if you want to do binary XOR, please do it. Majority of C, you can have it. You can even lift them with a constant size indexing gadget or something, anything. Is it true that PCR space is lower bounded by the black-white Pebling price or not? Functional pigeonhole principle. That's really like, we know now by Galesi, Kolodjeshik, Tapan, where do we stand? We have a square root n lower bound. It would be very surprising if that was the right answer. But somehow, all the techniques we have developed so far just fail for functional pigeonhole principle. And then also, I think total space for PCR or even PC without Euler variables. I don't think we know anything about that pretty much. Okay, so that's an overview of what is known, like a whirlwind tour. And now we're going to focus on proving lower bounds for random force CNF formulas. Any questions on the overview?
When you're saying that the lower bound strategy fails for the functional feature on principle? Like, does it fail immediately for obvious reason, or we need to unpack?
Again, so we need to build the way Bonacina and Galesi works. They say basically they have this combinatorial game.
Yes.
Between, you can think of it as a, if you're into Ehrenfurst territory, it's some kind of version of that maybe, where you have like a spoiler and a duplicator. And as usual, the duplicator strategy will give you a lower bound. They're not quite spoiler and duplicator, but there's something. There's some kind of, there's an upper bound guy and a lower bound adversary. And the lower bound adversary is like the good guy, that's us. So if we have a strategy to play this game indefinitely, we have a lower bound. Okay, and then they just say, okay, good. You look at this game, and then you see that this game immediately implies space lower bounds. So now you can just ask for any CNF formula, can we play this game? And then we can look at the functional pigeonhole principle, and the game is well defined, and the lower bound guy immediately loses.
Okay, so immediately.
I mean, you get nothing. You get
Okay.
Yeah. As far as I remember, like, do you get little omega 1? I don't think so. I'm a little bit on thin ice here, but I think basically you get absolutely nothing. Okay. Yeah. Other questions? So why is it hard to prove space lower bounds? So how do you do it for resolution? Well, for resolution, you're given this refutation. You have a bunch of clauses, or rather, actually what you do is you're giving, the way you do this, you assume that you're given a small space refutation. And now you build a partial assignment, and let me be a little bit fancy. You agree with me that a partial assignment is the same as a one CNF formula over distinct variables. Can you sort of see that mapping? I mean, the one CNF is the conjunction of all the literals set true by the partial assignment. So let me write it in that way for a reason that will become clear too. So you define, or you construct, a one CNF formula, dt, and it's going to have the following properties: that, well, dt is going to be satisfiable. It's going to be the case that dt implies ct. And then you need to be able to build this constructively. You're going to make sure that the number of clauses in dt is at most the clause space of ct. Okay. If I can do this, then clearly I'm home. Because then I would say for any refutation in small space, I just build these guys inductively. They're all satisfiable. And they imply CT, meaning that CT must also be satisfiable. It cannot contain contradiction. And then I use this whenever I need to do an update. I need to know that DT is not too large. When do I need to do that? When I do an axiom download. Because when I do an axiom download, I need to extend. I need to find a free literal that I can use to satisfy the axiom that was downloaded. And that is going to use expansion properties. And then I want to know that the sort of, it's going to be a bipartite graph argument, and I need to know that this set of vertices is not too large so that we still have expansion. Okay? For inference, what will I do? Nothing, right? Because we're just working with implication. The problem I have is, what do I do when I erase? Well, then at erasure, I know that dt minus 1 implies ct, but this is way too large, potentially. But what do I do? It's not too hard, right? I know that these are still clauses, so every clause in CT is satisfied by some literal. So just pick one literal per clause and shrink dt minus 1 to these literals. And then I maintain this. Am I making sense? Okay, so it's like dealing with erasure is an utter triviality. Is this making sense? Why does this fail? for polynomial calculus? Well, suppose for polynomial calculus, we start by doing the following. So I download an axiom, say x1 minus 1. And then maybe I download x2 minus 1, and I keep going, and after a while I've downloaded xn minus 1. What is the space of the configuration so far? 2 times n. How many literals do I want in my 1 CNF or in my partial assignment? Well, I can afford up to 2n, and I only need n, right? So we're in good shape. Now, we do some inference steps. And then suddenly, the prover just erases all of these. And why? Well, because it turns out that the prover derived this. x1 times x2 times xn minus 1. Note that I can definitely, I mean, these are essentially the same, right? This says that all of these variables have to be 1, which is what this says also. By the implicational completeness of polynomial calculus, I can definitely derive this. Okay. So now I need to choose very, very carefully 2 variables to satisfy this configuration. That's going to be pretty hard. Because this configuration forces all n variables to 1. And now my lower boundary. Am I making sense? Okay, so how can we deal with this? So what ABRW did, well, ABRW is a mysterious paper. They decided that the right way to think about this is to go into multi-value logic. And so you sort of lose track of, or at least I lost track of things for a decade, and it was kind of hard to see what was happening. So let me sort of give a high-level view of kind of what they do. Also inspired by, basically, you could say that what this first FLNRT paper did was like reading ABRW very, very carefully and saying, we don't like multi-value logic. Can we somehow please translate this back into 0, 1? And then you get the idea that you're going to do exactly, you do the same thing as before, but except that dt should be a 2 CNF formula over where clauses are over pairwise disjoint sets of variables. Pairwise disjoint sets of variables. Okay, that's the only difference. Everything else is supposed to be the same. And now it works. Okay, why does this make any sense? So firstly, note that I claim that this 2 CNF has to be satisfiable. Right? I mean, clearly it's in every 2 CNF, every 2 CNF has 2 unique variables that don't appear anywhere else. So it's definitely very satisfiable. I will also make sure to maintain this. This will be the tricky part, and we already know, like, where will the challenge be? We will still have the challenge that axiom download, we need to argue by expansion. That's basically going to be the same as resolution, except the parameters are going to be slightly more challenging. That's why for resolution, it's not so hard to get space lower bounds for 3 CNFs, but since we need better parameters for PCR, we get it only for 4 CNFs, unless we're willing to kill ourselves. But the interesting thing is this. So I claim now what has happened is we have strengthened our inductive hypothesis significantly. Because note here, we said that, oh, I know of a single assignment that satisfies my configuration. Now, suppose we have space S, then I'm saying, I actually know about 2 to the S different assignments, right? The Cartesian product for each clause. And all of them has to satisfy my configuration. So this somehow, you see that this gives me much, much more structural information about this beast. And thanks to this, this is the classic thing that we know, right? If you cannot carry out an inductive argument, strengthen your hypothesis. This is a very high level is what's going to happen. So now the plan is to take a step back, give you some quick definitions just to make sure that we agree on what random k-CNF formulas are. We're going to look at closed variable incidence graphs again, so maybe I'll say a quick thing about those. And then we'll talk about the technical tools we need to prove space lower bounds. We have identified two challenges. For axiom download, we need some kind of expansion argument. I'll state what this is, but I will not prove it because qualitatively it's the same thing as for resolution. The new thing and the hard thing is how to deal with erasures. And so basically what I need to prove is a statement that says, suppose that I have a set of polynomials P. So basically what I need to prove is a locality lemma. It's a locality lemma because that's what it was called in AVRW, and all other papers they differ in the technical details, but sort of the high level approach is exactly from AVRW, just stolen from there. And in particular, the technical challenge in every paper is to prove a locality lemma. It basically says the following: if P is a set of polynomials such that you take the monomial space and it's at most S, then there exists a row such that the domain size of row is big O of S, and row satisfies all the polynomials in P. This is what we need to prove. Note that we've seen that this is blatantly false. So this can only hold, we're going to use more, so we're going to say that P has been derived in small space. And then we're going to argue that thanks to the fact that we have a small space derivation, this false lemma turns out to be true. And it's kind of, I think it's hopefully, so maybe this is a good place to stop. Like, if we could somehow miraculously get this, then what you would do at erasure is you would just start to say your shrinking would be related to basically, I want to pick that row. And then continue. Kind of, sort of. Does that make some sense? So this is the whole challenge. Okay, so random k-CNF formulas, unless there are questions at this point, or like everything is crystal clear. Fantastic. So I say that F is a randomly sampled k-CNF formula from fancy style F with n variables, density delta, and for k-CNFs, if F has delta times n randomly sampled k-clauses with exactly, let's agree for today that a k-clause has exactly k-literals. So basically you just look at all k-clauses. So there are n choose k variable choices, and then you can flip the signs into the k bits. You're just going to sample delta n such clauses. Delta is going to be the density. That's called the density. Are you going to do it with or without replacement? Doesn't really matter, and you can make this formal in the sense that the probability distributions that we care about with or without replacements have essentially the same distribution in the range we're interested in. Just for concreteness, let's agree that it is with replacement. And then you can argue that for constant delta, you're not going to see any double copies. Okay. What do we know about such formulas? We know that for any k, there is a constant delta. For any constant k, there is a constant delta such that if you sample from that distribution f is going to be unsatisfiable asymptotically almost surely. So for k equals 3, it's enough to choose delta something like 4.5. As k increases, you need larger deltas. It's a long-standing challenge to prove that in fact there's a sharp threshold, that there is a delta k such that if you're epsilon fraction above, then you're asymptotically almost surely unsatisfiable, and epsilon fraction below, you're asymptotically almost surely satisfiable. It's a recent, or somewhat recent, I think maybe 4 or 5 years back, breakthrough that this is actually true for galactic K. For reasonable K, we only have upper and lower bounds. So for k-CNF, for 3 CNF formulas, I think the lower bound is maybe like at least 3, maybe 3.5. I don't know. Okay, and then again, the upper and lower bounds sort of, for any constant K, you have such bounds. So we are really going to look at GF, which is the closed variable incidence graph of a formula F. So just to make absolutely sure that we remember what that is, we have the left-hand side. Every vertex is labeled by a clause. On the right-hand side, every vertex is labeled by a variable. And the edges are all Cx such that the variable x appears in the clause C. Note that I throw away all information about signs. So this is not the closed variable incidence graph is not the one-to-one representation, but it somehow captures the most important things. And now we say that such a graph is an S delta bipartite expander. Since we have different expansion notions, let's just write this one down. Today we need a fairly simple notion of expansion today. No boundary, no nothing. We just say for all u primes, subsets on the left, such that u prime has size at most s, the neighbors of u prime on the right is at least delta times the size of u prime. Just looking at neighbors, not unique neighbors, not anything. Okay, this is all we need. And then we had a result that is, I guess, folklore, but I think the first time, or it's not folklore maybe, because it's in the paper that actually established length lower bounds, exponential length lower bounds for resolution. This is Severedi in 1988. Suppose that you have a fixed k that is at least 4, any fixed delta, then for all such k and delta, there exist lowercase delta and gamma such that if f is sampled from random distribution over n variables, density delta and k clauses, then, and you look at the closed variable incidence graph of f, then that will be a 2 plus delta, lower delta, gamma n expander. And what is important here, we really want strictly larger than 2 in the expansion. That's going to be important, and that is why we need k greater or equal to 4. We don't quite have this good expansion for 3 regular graphs. So what was proven by Bonacina and Galesi? Oh, there was one paper that I didn't cite in my overview. Sorry. So let me correct this and say that first we had this Bonacina Galesi paper, and then there's a long list of authors: Bennett, Bonacina et al. And I will not try to read out all the authors. BBGHMW. but Bonacina and Galesi are in there. So these two. So basically, what they proved is for any k greater or equal to 3 and delta is a constant, the monomial space in PCR of refuting f is linear, asymptotically almost Schrodinger. So the proof is essentially Bonacina Galesi, but they get it only for k greater or equal to 4. And then if you really squeeze the juice out of the argument, then you can bring k down to 3. But it's going to be a problem that the expansion is not good enough. So what we are going to do today is we prove this for k greater or equal to 4. We're basically going to follow Bonacina Galesi, except that we have a slightly more, a very like, so what happens in Bonacina Galesi is that there's a two-step thing. You take the formula and you argue about the combinatorial game. And then once you have the combinatorial game, you have a very abstract argument that, oh, this gives me a space lower bound. And you sort of don't see even in some sense, like what do these, what we're going to call these guys, I'm going to call them for shadow configurations. And it's very hard to see even what these shadow configurations look like. We know they're going to be two CNF formulas, but like, what are they even? So we are going to do a simplified exposition of this concretely for 4 CNF formulas or k-CNF formulas k greater or equal to 4 that makes all of this very explicit. So you'll see exactly what the shadow configurations are, and they will allow us to somehow get some understanding of how we're actually very concretely doing the load law. Okay, so let me tell you what our shadow configurations are. We're going to have, let me see if I can put the properties over here. Here are my shadow configurations. Let me call them. They're going to be throughout this talk. Whenever you see a fat style D, that's a shadow configuration. That's a 2 CNF formula. Fat style P is a polynomial configuration. So D is a 2 CNF formula. It consists of two parts, the K part and the M part. And we have the following. So we have that the clauses in Q are over distinct variables. So pairwise distinct. There is no sharing. So every clause in Q is over two fresh variables that don't appear anywhere else in Q. The same holds for clauses in M. Then I would say that for every X in a clause D in M, there is a unique clause C in Q that also contains X. So let me maybe see if we can make a small picture here. So here is M, and we have maybe a clause X or Y here. Let me ignore the signs for now. We have maybe also Z or W. This is another clause. And what I'm saying is now that when I look at Q, there's going to be a unique clause that contains X, and there's going to be another unique clause that contains Y. Maybe this is x or, I don't know, x prime, y or y prime. And similarly here for z, we have a z or z prime, and we have a w or w prime. And then we say for every C in Q, there exists a unique variable x in C that appears in a clause D in Q. Okay. So if I look at a clause over here, I see, oh, for this clause, there's exactly one of these variables that appears somewhere over in F. From this, what do I know? Well, if you just look at this picture, you realize that Q is going to be exactly contain double the amount of clauses in M. And you also realize that D is going to be satisfiable. Why is that clear? Well, just start by satisfying the M part. So just pick one literal here somehow. Then it's clear that, and it's paired up with two unique Q clauses. So once you pick the literal here, well, you potentially said, if I pick X, then I'm not free to pick X here, but I have X prime. And here I have a choice between Y and Y prime. So I first satisfy this with one literal, and then clearly I can satisfy this. Are you happy with this? Okay, and the size conditions. What do I want to say more? I want to say that Q are, okay, so maybe actually let me put a timestamp on this. So this is the shadow configuration at time t. So QT are subclauses of previously downloaded axioms. So somehow, whenever you downloaded an axiom, I say, okay, I can not only that I'm going to satisfy that axiom, but I actually commit to satisfying a two clause that is a subclause of this for clause. Okay, and this is how whenever I deal with an axiom download, I'm going to find a two clause like this. But then, you know, maybe I start doing derivations. So I'm going to call Q, let's say Q, that this is the axiom part. And M, I'm going to call the derived part, because then you maybe did some derivations and then you erased the axioms. And then I say, yeah, I don't know what happened, but they're not. So M is adding constraints on top of the axioms, but not too bad. In particular, you see that somehow you can, for every derived clause, you can pair it up with two axioms so that you can clearly satisfy all of these three, and they are satisfiable regardless of anything else. So I'm saying that whatever you can do in small space can be captured by something like this. So that is, what does this mean? Well, it gives us some kind of structural information, arguably. Is it clear exactly how to interpret it? No, but it does tell us something about these derivations. So what do I want to say more? The variables in MT in the derived part are from previously downloaded axioms. So M is not completely wild. It's like the intuition is that it's traces of axioms that I maybe had before. Importantly, we're going to make sure that if you look at the total number of clauses in D, that's going to be upper bounded by how many monomials I have in memory at time t. And the final property is that this configuration is strong enough to imply the polynomial configuration. So note now that, again, this gives me exactly this lemma that I told you about before. Like, suppose we can pull this off. Suppose we can build this kind of shadow configurations. Then this tells me exactly that, suppose you have derived a polynomial configuration in not too large space, and the whole derivation is in not too large space, then I only need to look at how many monomials you have. I don't care about whether they're high degree or not. Because I know by these things that I can, if the space is S, then just by assigning big O of S variables, in fact, I have a wide choice of how to do this, right? There's an exponential in S choice of different ways of assigning only S literals, and all of them will satisfy these polynomials. So in particular, you see that getting something like this is just not possible. Like, we're not talking even about contradiction. Any configuration where, like, I have, say, like a sum of high degree monomials minus a constant, like, you know, I could have like x1 up to I don't know, xn plus y1 up to yn plus z1 up to zn minus, I don't know, 42. This is also not derivable. Okay, or maybe change this to 2 if it's easy. 1 or whatever. Because this has only space 1, 2, 3, 4, but I cannot set 4 variables only to satisfy this. So nothing like this will be derivable in small space. And the fact that we cannot derive contradiction is just a particular corollary of this much stronger statement. Am I making some sense? Okay. So what do we need to do? Let us maybe let me again write down the 2 technical challenges that we face, and then I'm going to hand wave that we ignore one of them, and then we'll talk about the other one, and then we'll have a break. I think that will take us a few minutes. So note that inference steps we couldn't care less about. I mean, we're going to build these shadow configurations, spat style d sub t, inductively. And we have 3 things to worry about. Inference, axiom download, because they're in the inductive step, everything that happens is either an inference or an axiom download or the ratio. What's the base case, by the way? Well, the base case is we start out with an empty configuration, and you see that the empty shadow configuration will work perfectly fine. So the base case is already done. For inference, it's already kind of clear that everything is implicational. We don't need to worry about it. For axiom download, we need expansion, and in particular, we're going to need something that is called online matchings. Basically, we know, so what's going to happen here is, as the derivation starts downloading axioms, every time that happens, we're going to need to find 2 free variables, because we're going to pick, like, for every axiom download, we want to pick a 2 clause that is a subclause. So we need 2 fresh variables that are not constrained in any way. And we know that if it stands to reason that if the clause variable incidence graph is a good enough expander, then we can do this for a while. But now, obviously, what the adversary is going to do is going to download some axioms and see how we pick. And then based on this, there are going to be some strategic erasers. And then there are going to be some downloads of other clause vertices. And then if we're lucky, we can match those also, but we're slightly constrained by bad choices we made before. Okay, so now we're getting slightly uncomfortable, but we're still somehow managing. And now the adversary again does a strategic erasure, and now we're except for some choices that we really regret by now, and the adversary starts pushing in a third direction. And we want to be able to argue that we can maintain our matching not just in a single shot where we get like vertex per vertex. We know that by these peeling arguments we had before, we're sort of going to be able to maybe do it just in a one-shot argument, but we want to be able to do it repeatedly, adding, erasing. That's what an online matching is. So I'm going to state the property that we need, but this is qualitatively the same as for resolution, so I'm not going to talk about it. The erasure is the fun part, and this is where we need our locality lemma, which we already talked about. Okay? So let's see. So an online matching is precisely what I told you. We have, say, a challenger. Okay, so firstly, what's an R matching? Let me draw a picture of what an R matching is. So suppose I'm interested in this set in the graph, and R matching is, this is for R equals 2. Every vertex on the left is matched to 2 separate vertices on the right. So every guy, it's a set of edges where every guy on the left is incident to R edges. Every guy on the, what did I say? Every guy on the right, every guy on the left incident to R. Did I say that? Again, left incident to R edges. On the right, you're incident to only 1. So from the right side, this looks like the standard matching. From the variable side, from the closed side, we want to have R. We're only going to use R equals 2. So this is an R matching. The online R matching game is exactly what it sounds like. We have a challenger that basically says, in every round you do the following. Either you pick a vertex. I mean, this could be in general like a, any kind of graph. In every round, the challenger does one of two things. So the challenger picks a vertex, and then we, the matcher, we have to commit to, here I maybe pick, okay, now I'm going to pick this one and match. And then in the next round, the challenger picks maybe this one, and now I need to match, so maybe I pick this one and match. We're going to have an SR, so in this SR matching game, the edge set L satisfies that I have a total of at most S edges. So in particular, S is, you can think of it as always being a multiple of R. And the challenger, when you go above the budget S, then the challenger has to erase. So, maybe we're above budget now, then the challenger erases this, and then I just decommit and remove these. Which one? These. Okay, and then the challenger maybe asks for these again, and then I match with these. So this is the online matching game. The challenger wins if at some point there is, like for instance, maybe here. Let's see, do we have a winning position for the challenger? Let's make a winning position for the challenger. Suppose now we have this situation. Then if the challenger plays this vertex, then I cannot find, I have one free neighbor, but not two. So the challenger won. If, however, the matcher can play forever, then the matcher wins. Does this make sense? Then I can define what an online matching is. So an SR online matching is just a winning strategy. Okay? It's a collection. It's a collection of R matchings that has the following property. So the empty matching is in L. L is downward closed. What does this mean? Suppose that L is an R matching that is in L. Suppose that L prime is also an R matching and that it is a submatching of L. Then L prime is also in L. And then you have the extendability property that says, suppose that L is a matching in fancy style L, and suppose that the size of L is at most S minus R, then for every U that is in U, but not in L, we can extend L to an R matching, including U. It should be clear that this is exactly a winning strategy for the matcher. Okay, so an online matching is like a collection of matchings that you can maintain under additions and erasures, up to at most S edges. Am I making sense? So now, what we're going to prove, actually, our result is going to be something like the following. Suppose that F is a CNF formula such that the closed variable incidence graph G sub S has an S2 online matching. Okay. Any CNF formula with this property, I claim that the monomial space in PCR of refuting this CNF formula is at least, I'm not going to kill myself with constants, but S over A we can get. Okay, and now I just need to argue that so we're going to use a theorem now to get our k-CNF lower bound. We're going to use a theorem that goes way back to Feldman, Friedman, and Pippenger, all the way back from '88. And just to note that, by the way, Pippenger is one of the guys who did like some of the early work in Pelling. So, say Nick Pippenger. So Nick and his friends proved that if G is an S R plus delta bipartite expander, where I'm assuming that lowercase delta is some positive constant, then G has an online matching. Okay, it has an R online matching. So R is the same R that is the expansion factor, and then how much above R you are, you're going to take a hit in that. So you're going to get S times delta over 2. So if we, if delta is going to be ridiculous, this is going to be ridiculous, but it's still linearness. And now all I need to do is basically, okay, so now if you just put things together, that means that sample a random 4CNF formula, it will have at least this good expansion. So it has an online matching. So if I can prove this, you should be happy with the polynomial space global. Okay. So And in particular, to deal with axiom downloads, it's hopefully kind of clear that this, like, what will you do whenever an axiom download comes along? Well, you will somehow reduce it to a challenger move, and you'll use the online matching game to find two free variables, and those give me a two subclause of the axiom clause, and that's what I'm going to put in Q, pretty much. Maybe we should write down the details after the break, but this is roughly how it's going to go. So let's write down the locality lemma, and I maybe want it on the board. I think we're done. We know what random k-CNFs are and closed variable incidence graphs. Yes. Well, let me keep the locality lemma over here. This is what's going to be the most fun, but it's a very short statement. Suppose, with all assumptions we've done so far, in particular, I want. No, actually, no. So the locality lemma says the following. Sorry, I take this back. So the locality lemma is. Yeah, let me state it and then we can talk about what it says. Sorry. So P is a polynomial configuration. And suppose that D equals Q and M is a shadow configuration. What do I mean by shadow configuration? Well, you have it over there. Those are the formal properties. And suppose that I say that happily D implies P. Okay, then I should be happy, except the problem is now obviously that we're right after an erasure step and D is way too large. So like everything was fine before, the polynomial calculus derivation did a wild erasure move and I still have my D, but it's like it's far too large. Then the locality lemma says, fear not. It says then we can find a shadow configuration D prime, which is Q prime and M prime, which has the following properties. First and foremost, D prime will imply P. How will I pick? Remember, these are sort of subclauses of axioms, and to make sure that I maintain this, I'll somehow intelligently pick a subset. And then I somehow pick an M also, which will have to work a little bit harder. But I'll make sure that M is at most 2 times the monomial space of P. And note that at this point, so I got a little bit confused. The only assumption that we're using is the only thing we know about P. Actually, we have no history. We don't know how it has been derived or anything. I'm just promising to you that P is a polynomial configuration. It has a shadow configuration that implies it of some size. Then D prime is a small enough shadow configuration that implies it. Because note that the size of D is bounded by the size of M, which is bounded by 2 times the size of M. So this is going to be like, yeah, I guess the number of, so the number of clauses in D is going to be something like 6 times the number of monomials in D, something like that. So maybe this is a good time. So what I want to do now is give you a break, I think. What are we going to do after the break? After the break, I want to argue, maybe it's worth doing, I want to prove that if we have an online matching, and if we have this locality lemma, then we're done. We're going to run through the inductive construction. And then the whole crux of the matter is going to be, yeah, but how do we prove the locality lemma? Okay, and that's going to be after the break. Do we have any questions before we take a break? then let's just have some time to think about this over the break. So we are back after the break, and we want to prove, we're assuming that the locality lemma holds. Again, that if P is any set of polynomials, and I just say that it has a shadow configuration such that D implies this set of polynomials, then I can shrink the shadow configuration or actually rebuild it slightly to get a new shadow configuration D prime that also implies P and that has the right size. Given this, and given that F is a formula such that you have a winning strategy in the online matching game, you have S2 online matching, then I want to argue that you get an big omega of S lower bound, S over 8, but we're not going to sweat too much about the constant. There are a few things that could be tightened. Like, I think essentially S over 4 you should be able to get if you just look at what I'm doing and do it slightly more carefully, but I really don't care. Okay, so let's fix an online matching. We're assuming that the locality lemma is true. We're assuming that we have an online matching. So fix an online matching, fancy style. Fix a polynomial calculus derivation in small space. We're going to build shadow configurations such that the shadow configuration D at time t implies the polynomial configuration pt. And the M part, this part of the configuration, is not too large. And note that once I have a handle on the M part, the Q part is at most twice the size. And this is because of these properties. Let us repeat them again, in particular because I screwed them up before. For these clauses, like all of these clauses on the M side are over pairwise disjoint set of variables. The same goes for the Q side. The Q and M share variables in a very specific fashion. Namely, I can pair up every variable in M with two variables in Q, such that both variables in M, like the one variable appears in one of the Q clauses and the other variable appears in the other of the Q clauses. And because of disjointness, this is the only sharing. Clearly, these two Q clauses cannot share anything anywhere else with M, because there are pairs of Q clauses that have this sharing with a particular M clause, and because of disjointness, there's no other sharing. So this is going to be important for us. We can satisfy these sort of triplets of clauses in isolation. And here, I haven't, here everything has the same sign. I really don't care about signs. So you can use negations. In fact, one piece of notation that we're going to use, I'm going to write x to the b just to be the literal that is satisfied by sending x to b. Just this piece of notation. So and then so the signs are going to be in the exponent, and I really don't care. This could be like a, this could be b, this could be c, d, e, f. I don't care about the signs at all. They're totally uncorrelated. All I care about is this variable share. Is this kind of clear? It's not clear why we're interested in this, but what the structure is. Okay. And importantly, it's going to be very important that I can build an object like this that implies my set of polynomials. And somehow the intuition is that, well, if my set of polynomials is implied by a beast like this, it cannot be too over-constrained. That's what I want to say. Okay, so I want to build shadow configurations. In order to help me do so, I know that all the QTs are subclauses of axioms. Let me keep track explicitly of which these axioms are. So I have a bijections between QT and the axioms AT, where the bijection is the natural thing, right? Every QT, every clause in here is a subclause of a unique guy in here. I just pair them up. And then what I will do is to deal with the axiom downloads, I will maintain a two matching on AT. Let me give that a name also. That's L sub T. Okay. Fantastic. So where are we? Now let's see why this is all we need. So suppose we do now an axiom download. So we're downloading, an axiom download of an axiom of a polynomial P sub B, which is like the clause B. Okay, let B be an axiom clause. And let's get the trivial cases out of the way. Suppose that B is already implied by D sub T minus 1, then I don't need to do anything. And I copy everything. So the interesting step is when assuming that D sub T minus 1 in fact does not imply B. Then that means in particular that note that implies that B is not in A sub T minus 1. Because if it was, then QT, which is a part of DT, would definitely imply it. Okay? So it's a clause outside of the matching, and we have space, like if you look at LT minus 1, you're going to see that, okay, so this size of this matching is 2 times AT minus 1. AT minus 1 is the same as QT minus 1 because it's a bijection. And now this is like 4 times MT minus 1. And then by the invariant here, this is at most 8 times the monomial space of PT minus 1, and we're about to do an axiom download, so this is clearly at most 8 times S minus 1. Sorry, hang on. This is at most S over, we're about to do an axiom download, so this is like, this is at most S over 8 minus 1 times 8. How did I? So we get something like S minus 8. There's plenty of space, right? We could play the online matching game actually 4 times if we wanted. So let's play just once. But I know I'm going to use later that I could play it 4 times if I like, or at least, you know. Let's play it once. So we do an online matching. And that will give us 2 fresh variables, X and Y. So that B is, they appear in B, right? So B is now X, or do I want the signs here? Yes, X to the A, or Y to the B, or B prime. This is going to be added to, I want to add this to Q. Right? Basically, there's one slightly annoying fact now. Q should have even size, so I need 2 clauses, right? So either the derivation is nice and it's now immediately downloading a second axiom, in which case let's just continue with that axiom download. What do I do if it refuses to download an axiom? Let me download an axiom myself. Okay. I claim that there exists a B star such that D sub T minus 1 union XA or YB does not imply B star. For B star, an axiom in F. Okay. Why? Well, I mean, suppose that this doesn't hold. Note that this is satisfiable. These are 2 fresh variables, so definitely the union is satisfiable. Okay, so fix a satisfying assignment of this, guys. If I cannot find a violated B star, well, then the formula is satisfiable, and then I think we can go home already because we have our space Lorba. Are you with me? Okay. So, but now play the online matching game again. And we get now that B star is, and let me try to be consistent with my notes, B star is now Z to the C or W to the D or B star prime. Not super beautiful notation, but maybe it's good enough for today. Okay, and now I'm going to set QT to be QT minus 1 and XA or YB and ZC or WD. Okay. MT is going to be MT minus 1 and I really don't care at this point. Like, I'm not using M right now, so I'm just going to do something crazy. Actually, sort of the only what I need, I just need it to have the right size. I need to make sure that DT implies everything before plus the new maximum, but these guys are already taking care of that, right? So let me just write something crazy. I mean, I don't know, X or Z, that's fine, regardless of this. I really don't care. LT is, the matching is LT minus 1. Union, well, I matched D to XY, and I matched B star to ZW, right? The notation is slightly informal, but I trust that you understand what I mean. And AT is going to be AT minus 1, plus I now pair up, obviously, I add B and B star. And it's clear that I'm going to pair up B with this guy and B star with this guy, yes? Okay, so this completes the inductive step for axiom download. Are we happy with this? So I claim that, let's check, what do I need to, I maintained A, I maintained the matching, I grew the size enough. I mean, because P, I did a download in P, so I got, well, for a CNF formula, if you were doing in PCR, the space grew exactly by 1, which means that M could grow by size 2. It only, not that it factually only grew by size 1, so I'm even good. Like I have some slack here in this part of the argument. And the thing I really cared about is making sure to imply B. And I did this because don't see now. I did this before because Q contains this now. Right? Are we happy with the inductive step? Okay. So next step, inference. Do nothing. The only thing I need to worry about is maintaining, well, implication is by soundness of the proof system. The size is increasing, so if I was good before, I'm clearly good now, and I'm not touching anything else. Yeah. Erasure is the hard thing, except that we're cheating. So we have now that D sub T minus 1, we're going to cheat, right? We know this. Because D sub T minus 1 implied already before erasure. So it definitely implies after erasure. Okay, so then this D is D sub T minus 1, P is PT, and you guessed it, I guess that, so we're going to appeal to the locality lemma. And we're going to set D sub T to be D prime in that lemma. The lemma tells us that the size condition is satisfied. The lemma tells us that we have implication. And the lemma tells me that I'm picking out the subset of the subclauses of axioms. Which means that I just, I have A sub T minus 1 and I have L sub T minus 1. And if you just tell me, it's sort of clear by this bijection here, which Q primes I have left, I'm going to take the corresponding A primes and L primes. Is this all making sense? I'm saying this a little bit quickly. Should I say it again? Or it's fine. So basically, since I'm picking a subset of the sort of the two clauses shadowing the axioms, I just pick those corresponding axioms and that corresponding match. Okay, but then this shows that by induction, if the monomial space of pi is less equal s over 8, we do have that d tau implies p tau, and d tau is satisfiable by construction, and hence it cannot possibly be the case that contradiction lives in p tau. QE. So we have, again, what do we need to do? We're assuming two things. We were assuming the online matching lemma. The online matching lemma is kind of fun. I mean, because what you're gonna, so how is the proof gonna go, right? You're gonna start by expansion. You can always play. But now the problem is that somehow what you're gonna do, think about this. One way to think about this is that you're not only going to answer to the challenger questions, but you're going to think a few steps ahead, right? You're going to realize that we played like this, and you see which guys outside of the matching are already going slightly low, right? So you say, oh, I hope that if challenger asks about this vertex, then I'm already fairly constrained. So in your head, you already commit to that. Well, if I get a question about that, I'm going to match it to these two on the right. Okay. And now you say, oh, but that may be constrained something else. Now I see that U prime, if I would get that question, then U prime would also be in bad shape. So then you commit to U prime also and say, well, in that case, I will match U prime to those two guys. And you keep going until everything is super unconstrained. Okay. And now and this is actually, we've seen this before, if you remember. We're sort of doing this kind of closure operation that we did in polynomial calculus. It's all the same. It's there are a lot of things that keep reappearing in subtly different, but sort of fundamentally the same shape. So we're basically going to maintain some kind of closure operation so that inside the closure, we have critical questions where we're very constrained how we can answer. And outside of the closure, we have excellent expansion. And then, of course, anytime if we get a question inside of the closure, then we already know how to answer. And if we get a question outside of the closure, we answer, however, because there's so much slack. And then once we've answered, we check, is there anything else that has become too constrained now? So we're always going to maintain like a super two matching of the actual two matching. Maybe it depends on the scribe energy whether we will have this in the notes or not, or maybe we'll just or there's a fairly nice. There will be soon. What year did I give? So we're following LMNV. I don't remember what year I gave. That's actually LMNV 26. I don't know if I wrote 25. So that's a paper that's going to appear early next year, hopefully. And then you're going to have in an appendix a write-up of this online matching game. So let's focus on the locality lemma. And again, because that's the fun part. So the locality, the online matching is sort of, you already needed to do that for resolution, but then you only needed a one matching. For PCR, for some weird reason, you needed two matching. So let's do the locality lemma. I'm going to need Hall's theorem, except I need Hall's theorem for two matchings. So I'm going to claim that look at a bipartite graph, UVE. It has a perfect two matching that matches everything in U. I claim, if and only if, for all subsets U prime, the size of the neighborhood of u prime is 2 times u prime. Okay, and I claim this immediately follows from Hall's theorem. One direction is obvious. Suppose that there in fact is a perfect 2 matching. Clearly this condition holds, yes? Okay, how do I do it in the other direction? Well, in our heads, let me quickly change. So I have my graph now. G, here it is. Here are the u vertices. And, you know, maybe I have something like this. Here are the v vertices. So what I do, quickly, inside my head, I clone every u vertex into 2. And then let these vertices like inherit the neighbor structure. So here I clone. Okay, so here's like u prime and u double prime. Yes? Okay, now if you think about it for a minute, you realize that this cloned graph satisfies the Hall's condition. So clearly there is a matching. Okay, great. So let me find the matching. And once I have that matching, let me merge back again. And, yeah. Okay, good. I'm not sure if you would get away with that proof if you were an oral exam for me, but you know, I'm doing my oral exam for you, and you are so nice, so you're buying this, for which I'm duly grateful. Okay, where do we have the locality lemma? Now let's make sure to have some space. So we're going to prove the locality lemma now. And we know that if I can prove the locality lemma for you, then we can go home. Then we deserve our Christmas bake, because then the locality lemma is everything that's missing for our lower bound. Yes? But hopefully, I'm hoping that it's maybe not entirely obvious why the locality lemma should hold. Or if it is obvious to you why the locality lemma holds, please write it down and simplify this. Okay? Because what I'm going to give to you, I'm a little bit short on intuition. Okay, let's just put it down. Where do I want to be? Okay, so my plan, the plan of the proof is basically going to be, I'm going to identify a part of the shadow configuration, let me call it D1, that I can keep. Intuitively, it's going to be, locally, it looks like it's small enough. And then I have to look at the part that is too large. Then I'm going to build a bipartite graph with U being the monomials in P, and then I'm going to do some matching magic. To build a new shadow configuration. A new shadow configuration. And now I'm thinking how I want to do this. Okay, maybe let me try. So here is my bipartite graph. Let me write over here maybe. Okay, the bipartite graph is H, U, disjoint union V, comma E. Let me tell you, U are going to be the monomials in P. I already said that. Okay, so let me do a proof by picture. So we have like M1 here we have M2. This is going to be a fairly large picture, so maybe I'm going to be lazy and only do 4 monomials, maybe. Let's see if we can get away with that. M1, M2, M3, M4. So this is U. V is going to be the clauses in M. So I'm not sure if I'm going to give them names. See. Here is maybe a clause, here is maybe a clause, here is maybe a clause, and here, and here, here, and here. And now I need to tell you what I'm going to do about the edges. And let me say that this is the clause CM. Let me say that that is X prime or Y or Z prime. Let the clause DM here be Y or W, right? This is what these clauses in M look like. So this is M. But now we know that M has this pairing with Q. So let me also put Q here. And then we know, right? You remember that there's this unique pairing up of these guys. So let me keep that in mind. Okay. And in particular, just to see what this might look like, here we could have, maybe X. Let me give names to this. I'm going to call this C prime is paired up with CM is paired up with C prime M. And C double prime M. And they look something like, suppose that this is X to the C or X prime to the D. This one is maybe Z to the E or Z prime to the F. And here we have maybe Y or Y prime. Here we have maybe Y or Y prime. I should be consistent and give them names. D prime and D double prime. It's Y or Y prime, say. Here we have W or W prime. And now, because it's going to be like, again, this clause has exactly one variable in this clause. You see that's X prime. It has exactly one variable in here, that's Z prime. And here we have Y in here. And here we have W in here, right? So something like this. And now the question is, what are the edges? And what I'm going to do is I'm going to add an edge. Okay, again, so I'm going to add an edge from M to C if, note that C is paired up with C prime and C double prime, yes, in Q. Let me look at those. And let me look at the variables in M. If M mentions any of the variables over here, then I'll draw an edge. Okay, so maybe I get something like this. And now let me see, I want something like this. maybe something like this. Okay, maybe that's my graph. So far, I'm just constructing the graph. Are we happy kind of with the graph construction? So again, these are just the monomials in P, the distinct monomials in P. These are the clauses in the M part, in the derived part, except for reasons that are not entirely clear, but maybe let's see if they become clear later. This clause in M is paired up with two clauses over here that mention two extra variables. So this guy identifies four unique variables over here. If any of those four variables appears in M1, then I'll draw an edge. So pen-related. Graph construction is clear? Okay. So fix U prime in U to have maximal size such that the neighborhood of U1 is at most 2 times the size of U1. Is there such a set? Yeah, I think so. I mean, the empty set definitely satisfies this. Maybe I can pick it larger. So let's see if I can identify it over here. Now is like where it's interesting. I think if I did this correctly, maybe if you cut me some slack, or I might have to add some edges. I think this is U1. Or do I need to add more edges for that? And this would then be the neighborhood of U1. Let me see. So now I want to see, because if I add this guy, then I will now pick up like 1, 2, 3. Maybe I need some more of these. This, maybe I need some more also. Let me draw this. I think I'm hoping now that M3 and M4 would like break this property. This seem believable, or do I need more edges? This one is adding 4. This one is also adding 4 together. They're adding, I guess, 1, 2, 3, 4, 5. Okay, I need one more. Now I think I'm okay. Something like that. I mean, you get the idea. And now, note that observe here that locally, this guy is not too large. I mean, this is an M part with an associated Q part. So I'm going to say that let actually this be M1. Let these guys be Q1. And I'm gonna say, let's keep M1, which is the neighborhood of U1, and Q1. And let me introduce notation. This mapping, let me just call it Q. It's gonna be convenient. So like, if I plug in a bunch of M clauses, Q just tells me which these guys are. Okay, so then this is well defined, yes? And note that locally, this is all looking fine. In particular, suppose that I am so lucky that U1 is equal to U. Then what do I know? Then I can go down. Why? Well, look at the size condition. The size condition is fine. What about the implication? Well, note that all variables mentioned in P apparently live inside Q1. And I know that all of D implied P, but the part of the if this holds, then whatever part is outside is like, I mean, it's mentioning variables that are not even there, right? So somehow there D might contain more, but then it's over a variable that do not even appear in P, and so we're fine. So I claim that if U1 would be everything, then we're done. Are you buying this? Yes. Okay. You don't dare do otherwise. Okay, so but now, okay. So hence we're saying no. We're supposing that this is a strict containment. And now I'm going to set U2 to be U minus U1. I'm going to set M2 to be M minus M1. And Q2 to be Q minus Q1, obviously. And then just D2 is going to be Q2 and M2. And this is the part that is too large. But here is the point. Note that I know that for any U prime in U2, what do I know? If I look at the neighborhood of U prime and intersect it with M2, I know it was too large to add. In particular, it was contributing, well, it's a strict inequality, but I don't need that. This must hold, right? Because suppose this didn't hold, well, then we would have thrown it into U1. Okay, but that means now that there is a matching. There is a two matching even. So let's fix it. Let's suppose that M3, which I rechristened to M, is matched to these two guys. And, M4 maybe matched to these two guys. And I'm able to match everything. Are you with me? That means that in particular, M has some variable in here, and M has some variable in here. Yes? Okay, so let's suppose that M is equal to, let's suppose it's equal to x raised to the power of A times y raised to the power of b. Note that these are signs now, because we're multilinear. Times m prime. M prime. Where, okay, I need some color coding here. So this is important. And I'm going to say, note that this corresponds to this guy and why I picked up do this correctly. Yeah, this guy. Okay, so now what I'm going to do is I'm going to build a new M. I decide that XM is a new 2 clause, and it's going to be X to the A or Y to the B. Note now that this, interestingly, this clause, I'm going to place it in M. And it is, so let me maybe, where am I? let me draw it. I'm sort of going to put it here maybe. So X A or YB. I need to pair it up with two Q clauses. There are two very natural choices, right? Why don't I pick this guy and this guy? Is it clear what I'm doing? So okay. So I'll do this now, the same thing for M. It turns out that this is like, I don't know, this is something else. I find two clauses and I match them up. And so I do this for every M in U2. And then I set M prime 2 is going to be, I look at all the monomials in U2, and I take this clause XM. Q prime 2 is going to be and over, again, all M in U2, and the Q clauses for XM, which are these blue matchings. Is it, I mean, is it, we're doing it by picture, but it's fully general. So are we happy with this, or should I take a step? No, you're fine with this? Okay, good. And then D prime 2 is going to be just Q prime 2 and M prime. Okay, let's check what happened. I claim that Q prime. Oh, and finally, sorry. Now the final punchline is now we're done. I'm going to set D prime to be D1, the part that I kept, and D prime 2, which is the new part that I did. Now I claim we're done. Now we can go home. So what do we need to verify? We need to verify the implication. We need to verify the sub-axiom clause containment. We need to verify the sus. Right? I think that B. Okay, let's maybe make the let's mark it over here even. Any one of these that you're happy with? I would say that the fact that I've just picked a subset of axiom subclauses, that's kind of clear. You're happy with this? I mean, I'm just picking out these unchanged. So clearly here I picked everything, but that lives in Q. And here I built a new clause. So M prime is not contained in anything, but for Q prime, I'm just picking out clauses. You're happy with this? Okay, let's look at the size. So we need M prime is, well, the size of it is M1 plus the size of M2 prime. I know M1, I know that it's less than 2U1, less equal, right? That's why I picked it. What about M2 prime? Here I'm actually matching the size of U2, right? So this is at most 2 times U1 plus U2, which is 2 times U. We're happy with this? Check on this. Okay. So, but does anyone have any suggestions how we're going to prove this? Because this is somehow the mystery. Like, why? Or at least it's a mystery to me. So again, this is the part where I say, like, if you really understand this, then you should prove some PCR space lower bounds very good. So let me clear out this thing also. So maybe let me tell you what the strategy is. It's a very roundabout strategy. Let me tell you what I want to do. And then I want you to agree that if I can do this, then we're done. And then let's see if I can do it. Okay? So we want to prove, we want to show, we are left to show that D prime implies P. And that is not a priori obvious. So basically, we're given any alpha such that alpha satisfies P prime. What I need to prove to you that alpha makes all polynomials in P vanish. Okay, so I'm going to do the following. I'm going to build another assignment, beta, with two properties. Beta will satisfy D, our original shadow configuration. And then I'm going to prove that for every monomial M in P, beta of M agrees with alpha length. Then I claim that in that case, like if alpha and beta, well, note that, okay, so note now that I know that, then I claim that alpha of P must, since they agree even on a monomial level, then definitely they assign the same truth value to all the polynomials in P. Yes? But beta satisfies the original D. So beta definitely satisfies P. Okay? So if we can prove this, we're done. Am I making sense?
Yeah. Why?
See, I don't, right. So yes, this would work, but why are we doing this? Because we can.
Okay.
And because we cannot do anything else.
Because a priori beta and alpha don't agree variable level.
We're going to build alpha. I mean, the whole point is now, like, if I can do this, then, okay, at a very high level, so, okay, so what's the plan? Maybe you know, I'm spoiling all the fun now, all the suspense, but basically you're given alpha, and it assigns everything. And you're going to look at, I mean, this part we have no understanding, like the D1 part. We have not analyzed it in any way. So here we're basically just going to say, let me copy alpha. I have no structural information. Okay. But note now that suppose I do this, Now I can get slightly nervous because these variables are now going to affect these monomials in ways that I don't understand. But now I'm going to basically say, well, the point is now that if I can just make sure to satisfy the new M clauses in some way, like I know that alpha satisfies the M clauses. And from a satisfying assignment, so alpha will satisfy this and this and this. And now there will be enough slack to also then satisfy this and this and this and this. And why am I not worried about what happens to M? Well, because it's true that you can have a lot of weird influences here. But look, if I'm satisfying this clause, then what happens to M? It vanishes. So I don't care about the assignment on these edges. I'm just basically here, I'm going to do whatever alpha did. And here I just go completely crazy. I just say, all these polynomials, just zero them out. And you're like, wait. What if, is this a good idea? What if I have a polynomial like 1 plus M3 plus M4? I don't care, just zero it out. That's not going to happen. In particular, any monomial 1, any constant monomials, if you think about it, they live up here. So somehow the alpha is going to take care of those. And here I'm just saying, so this is again structured information. Like, how am I going to satisfy? I'm just going to say, well, if you ended up down here, just zero it out. And it's going to be safe. Which is a pretty crazy thing to do, right? I've removed, note that these guys appear in polynomials together in some highly structured way. I'm just completely throwing away the structure, and I'm saying the monomials down here, I don't know about them, but I can zero them out, so that's what I'm going to do. Like, wait, yeah, but hang on, like which polynomials are they appearing in? How are they related? I don't care, just zero them out. And say a prayer that this works. That's going to be our plan. Okay, so let's carefully execute this. Let's see if we can do it. So we're given alpha that satisfies D prime. Okay, fantastic. So I'm just going to define first. Let me define beta 1 on all the variables in D prime. Note that we built D prime, and we're going to define beta prime to agree with alpha. Okay, now the problem is, now let's look at what do we have now? Well, we have the guys in D prime that do not appear. The guys in D that do not appear in D prime. We're going to construct a beta 2 on the variables in D minus the variables in D prime. And note again, the problem here is that I don't get to set all of the variables in this monomials. Alpha might set tons of them, but I'm just going to make sure that I have enough variables left over here to sort of patch these things up, and then I'm trusting that alpha made sure to zero out this monomial, and I'm going to keep that. Okay, so let's look at any clause C that was in M2, like one of these guys, the original C's. Suppose that C is some xg or zh or whatever. In the original configuration fat style D, I can look at what Q clauses it was matched to. Let's suppose that this was xc or x prime D, ze or zf prime. Okay, and I think Okay. So now I have two cases. Case one is, what if C was one of the clauses that actually got matched? Case two, what if it wasn't? Case two is going to be easy. So let's look at case one. So case one is that C is matched with some M in U2. So let me then call it Cm. I know, okay, that means that vars Cm intersect vars Xm. Is at most one, right? I know that I'm picking out M was matched because of one of these four variables, but I actually don't know that they appear in here, but at most one of them. By the way, I realize now I'm looking at my scribe now, I'm claiming equality. I think that's wrong. I want this. And if I now look at the two matched clauses over here on the Q side, I know that I picked, here I claim equality. I know that I picked exactly one of these clauses. Okay, so this I know. Suppose that this guy is in Q prime. Then what do I know? I know that alpha satisfies C prime M, so I'm not going to mess with that. But now let's look at beta 2. And I'm going to pick where there's one free variable. So in particular, so just to carry over the legend, apparently this one is the guy in Q prime, right? So I don't dare touch those variables, but I can touch these. The Z variables are free. And one of these live in here. So let me fix that guy. So let me set Z to H. That takes care of this guy. And now this guy I don't need to worry about. And here, let me pick Z prime and set it to F. That takes care of this. And note that these variables will now appear nowhere else. And very importantly, I did not mess with alpha. Alpha was setting these two guys, so I just stayed out of the way. Okay, case 2 C is not matched. Well, if so, life is easy. I mean, so we're living somewhere here, right? Or actually, let's pick this guy up here. So C is not matched. Here we see. Well, then we have free access to all of these variables. So let me just set, I don't know, let beta 2 be, in this case, I mean, X could be sent to G. X I send to G, okay, but then I'm not in control of this variable, but I'm in control of X prime. So let me send X prime to D. And then, I mean, here I can choose whatever I like. Let me choose Z maybe, and send it to, oh, no, I still chose Z prime and send it to F. I mean, I can do whatever, I can satisfy both. Okay. Now there are a bunch of variables that I'm not assigning. So now let's just say to get total. Now I actually don't care at this point. I think to get total assignment, extend beta 2 to agree with alpha on unassigned variables. And set beta to be beta prime union beta 2. We're operating over disjoint set of variables, so we can take unions of assignments. Yes? Okay, and now we're kind of done, I think. Let's see. So let's see. Let's look at beta 2. Beta 2 satisfies all of D minus D prime by construction. Beta 2 satisfies all of the old clauses that didn't make it into D prime by construction, right? I mean, for the match clauses, we satisfied this. We didn't touch this, we satisfied this. We satisfied this, we didn't touch this, we satisfied this. For the non-matched guy over here, we just said whatever, satisfy this, satisfy this, satisfy this. Are we happy with this? Okay. Now, beta 1 satisfies the intersection D prime, also known as D1. How do I know? Well, because beta prime agrees with alpha on these variables. Okay. Okay, so now I have concluded that beta union of beta 1 and beta 2 satisfies our old shadow configuration flat style D. Are you buying this? Again, I looked at, first I say, what part of D is not in the new guy? Beta 2 takes care of that. And then I say, well, what is in D prime? Well, alpha is taking care of that because alpha is satisfying D prime. So the union of these two certainly satisfies everything. Okay. Okay, good. We're making progress. If you look at the variable set of U prime, that lives in the variable set of D. The variable set of U1 lives in the variable set of D1 simply because of how I constructed this. That's how I mean, any variables that appear in Q over here will cause edges, right? So definitely, so alpha and beta agree. I don't know what it sets the monomial in U1 to, but I'm copying, beta is copying alpha on these variables. So whatever values I have here, by construction, they're the same. Okay. And now the punchline is that for M in U2, I know that beta 2 of M is equal alpha of M is equal 0. Because sorry, beta should be here. Well, let me write beta. I'm getting confused now whether it's beta 1. No, it's actually beta 2. It's okay to write beta, but beta is also okay. Because again, I'm not touching. Why do I know this? Well, because beta is not touching these blue guys, which are assigning in particular these variables, which are in particular satisfying this clause, which means that they're zeroing out this monomial. Okay, but now we can draw our QED box. Because this is exactly what I wanted to prove. I've established now that for all monomials, first I looked at, again, let's just say this one single time. I know that for all monomials here, alpha and beta agree because on these variables, these monomials only mention these variables. Note that there are edges going in that direction, but there are no edges going in this direction by construction. So when I assign these variables, I fix the truth values of these monomials, and alpha and beta by construction agree. Okay? So alpha equals beta on this part by construction, and here by construction, alpha and beta both zero out all M. Okay, so this means in particular that for all M in P, beta and alpha agree. So alpha of the polynomial configuration must be whatever beta of the configuration is. But since beta satisfies D, and D implies P, apparently beta of P is true, and hence alpha of P is also true. And note that alpha was an arbitrary truth value assignment that satisfied D prime. So any alpha that satisfies D prime also has to satisfy P. And that's what we want. Done. And now we deserve the Christmas break. Questions before we call it a day? Or comments or anything? I want to stress that I think this proof is deeply mysterious. And I wish I had a better understanding. All I can say that even getting this far, I think is, I mean, you can, I think we, again, the sort of, we extracted some kind of intuition here because we're seeing that again, what do we know about the shadow configurations? Over here, we're kind of keeping track of the axioms we've seen so far. And then over here, we're saying that, well, combining these axioms could have constrained things a little bit, but not too much. And then you can ask, is this a helpful intuition, or are we just sort of obstructing some other view? I don't know, but at least for us, we could not read this out of the previous papers for random casing. But now that you know this is state of the art. And now again, so one question for pebbling formulas. If you notice, we actually, what we did for pebbling formulas, we did not have a shadow configuration implying the configuration of clauses. We actually switched it around and said that the clauses implied something, and that's what we analyzed. I don't know for pebbling formulas whether you actually can maintain like shadow configurations. Some point many years ago, I believe that I had sort of proven that this is fundamentally impossible, but I no longer remember. So pebbling formulas are probably not amenable to this at all, except that this is going to be very vague, but one reason why the projection machinery fails is it also fails for these kind of weird configurations that have high degree monomials that are constrained by a constant term. This is exactly why the projection machinery that we did for resolution fails miserably for polynomial calculus. And somehow you need to argue also for pebbling formulas that in low space you cannot get such constrained high degree monomials. In that sense, there's some kind of, I mean, that's exactly the technical difficulty you run into. For the functional pigeonhole principle, or say for taking over 3 regular graphs, we don't know how to make this work because, again, somewhat similar, very high level now, but somewhat similar in spirit to what happened for coloring. What you can do here is that note that we can like localize and satisfy different polynomials without affecting other polynomials. Thanks to this structure, we have like a lot of disjoint variable sets. And when we assign these, they're not going to mess anything else up. The problem for functional pigeonhole principle is once you set a pigeon to a hole, then lots of other pigeons cannot go there, and it starts constraining things, so that somehow we're not able to carry out this order. Okay? And also for taking formulas in general, once you start setting a parity, parities start propagating through the graphs, and we're not able to do this. But note that, I mean, it's now, I mean, it's been a few years now, and we understand polynomial calculus better. We have coloring lower bounds that were completely beyond reach just a few years ago. So maybe now is the time to say we had a better understanding of polynomial calculus. Let's revisit pebbling formulas again. Let's revisit Seikin again. Let's revisit functional pigeonhole principle again, and just do something smarter. Or one thing you could also do, take your Christmas break, come back in January, look at the Galesi Kolodjeshek-Fappen paper that says that polynomial space is lower bounded by square root resolution width, get rid of the square. That's another option. But we will cover that proof. It will be, it's gonna be addressing some of the same problems, but with a different kind of machinery. They also have the problem of what do you do with high degree terms that you cannot afford to satisfy? And they have some very interesting notion of kind of making sure that these monomials don't take the wrong values, except I'm not assigning them, but kind of anyway keeping them under control, which we'll talk about in January. Yes, but I think any final questions before we call it a day? I should stop philosophizing. Then let's call it a day.